All right, so welcome everybody to today's Flow Talk. As you all know, or perhaps everybody, hopefully you do, since you logged in to attend the talk. This is a seminar series on federated learning called Flow, Federated Learning One World Seminar, and we hope to cater to all needs of federated learning community, which is growing very fast and is growing in depth and in breadth. Today, the talk will be focused on formulation of federated learning rather than, say, focusing on algorithmic development or systems or privacy and so on and so forth. So it's great pleasure to be welcoming Ahmed Khaled, who gave one of the first, if not the first, was it the first Flow Talk? It was the first, right? Suhaig, who gave it first, and now he's giving the last Flow Talk. Hopefully not the last, but the last so far. So now Ahmed changed location. He's a student, a PhD student in EC at Princeton, and we'll talk about recent work on FLIX. So Ahmed, go ahead.
Hi, thanks Peter for the introduction. So I'll talk about FLIX, which is a new framework for thinking about federated learning.
Would you be able to speak up a little bit? You might be a little bit too far away from the microphone.
Okay. This paper is going to be published in AI Stats of this year, and it's a joint work with Elmer Gasanov, who is a PhD student at KAUST, Samuel Horvath, also a PhD student, and Professor Peter, the host here. And it's available right now on arXiv, and hopefully like the AI Stats version will also like be a little bit updated. Okay, so what is federated learning, or what is our setting? So here it's a setting where data is distributed over many clients with potentially unreliable connections. This is sort of a very succinct or very short understanding of federated learning. Federated learning is like a combination of many fields, and it poses many interdisciplinary problems. So we have many clients, such as mobile phones or computers, connected to each other, and we want to solve a sort of learning problem using them. And this combines concerns from optimization, privacy, generalization theory, and so on. And it has many applications in mobile text prediction, in medical research, and other things. So the setting that we assume is a centralized setting where we have a central node or a server, and this server is able to communicate with up to n clients. So these clients can be computers, they can be mobile phones, they can be anything. And the central node, we assume it has access to all of them, or it can sample some of them. The formulation that people usually set federated learning in is the empirical risk formulation. And by this we mean that we're trying to solve this problem, minimize x in RT, where t is the model dimension, f of x, where we can write f as the average of the loss on each client. So n is the number of function, and this expression is the average of the losses on all of the clients. So we convert our machine learning problem to some sort of optimization problem, and then we solve the average of this problem on all the clients. So, for example, if like we can think of this perhaps as the difference between the predictions of some models, say linear regression or a neural network, from data on each client. So each client has its own data, and we're getting and we're counting that as the loss. So there are several challenges against the ERM formulation. The first of them is that usually in federated learning, we suffer from communication constraints. So in order to solve this formulation, information must be shared between the different FI. So like the clients have to share different information with the central node, and the central node has to share information with them back. So we usually have a communication budget, say of R times. And in order to deal with having such a budget, we usually apply some heuristic, something like we use an algorithm like fit average for R times. But it's pretty difficult to say what this converges to if R is not very large. Perhaps it would be better to have a principled way to handle such communication budgets. In other words, be able to tell whoever is trying to solve this problem or a similar problem or an alternative problem that if you do so-and-so steps of communication versus computation, this is how many functions you are able to. This is how much you're able to do. The second thing is that this formulation is agnostic to personalization. So by this we mean that here we find one model that we hope is good for all of the clients. And this is very unrealistic. We very rarely can find a model that can perform well for everyone. And as this very nice paper by Tayu, Eugene Bagdasaryan, and Vitaly Shmatikov shows, such model can often be even worse than simply not doing federated learning at all. So if each client just uses its own data to solve its own problem, then that can be preferable to federation. If by federation we mean that we end up getting one model for everybody. And this should make sense because these clients have different data. They do not have the same data. So for example, if these clients are mobile phones and the problem is mobile text prediction, then people write differently. Even the same language, even the English language, there's variation, regional variation in the way that people write English, and there's personal variation between people. And so the best predictor overall for the average is not necessarily the best predictor for any single client. So usually the alternatives to that is to use fine-tuning and personalized federated learning. And we will talk about these. So there is a very fundamental question in federated learning that we should be asking ourselves and that we should care about. Because there's a lot of work in the community about finding fast solutions for this problem, but we must ask is this problem a good model for federated learning? Is this problem what we want to be solved? So the question is, what are we trying to do? Are we trying to find a single model? Are we trying to find multiple models? How much do we care about communication complexity? And of course, is the training process private? Does it guarantee privacy? And we ought to think about like what is desirable in a framework for federated learning. So we're going to do some of just that. We will set certain desiderata for federated learning that we hope to see. So the first one is that we want it to be efficiently solvable. The empirical risk minimization problem that we had earlier has a very positive advantage. If each function is convex and smooth, it is very efficiently solvable. Even when you lose one of these, it's usually solvable for some metric. Hopefully new formulations can take advantage of this. And some formulations do not. So for example, if we use model agnostic meta-learning for federated learning, this can turn convex programs to non-convex programs. And this can sometimes incur worse dependence on conditioning, even when you have a sort of approximate convexity. So there's this paper by Ali Riza, Falak, Arya Mokhtari, and Asuman Ostalar on the convergence theory of gradient-based model-agnostic meter learning algorithms, in which they study the convergence of MUML. And this is one of the things. This function does not even have to be smooth in general. So we even lose smoothness sometimes. The second thing that we desire is that a federated learning should easily handle communication constraints. If I constrain the number of communications that I'm going to do by some budget, we should still be able to solve this problem for any budget and give a guarantee for that. And this is something that is only done heuristically in ERM. And the third thing is that we should also have built-in personalization. We can give a personalized model for each client. We avoid the one model fits all approach because it is not good. And we can easily accommodate new clients to the framework because in realistic federated learning, clients are coming and going all the time. Finally, if we have something that is also not difficult to analyze, this is better because we can study, let's say, other properties more easily. So here, I did not focus on privacy, but that is usually an important concern. Especially that we have to give theoretical guarantees for privacy, otherwise no one believes you. So now we can start on like the FLIX formulation, which I believe can answer some of these questions, or at least give a starting point for doing so. So for each client I, we have the function fi of x, which again, this function represents the loss on the local clients, on the local data on the client I. We define the best solution, xi, as the argmain of x of fi of x. So xi is simply the local empirical risk minimizer of fi. And this solution, it can be pre-computed prior to the start of the optimization process. It does not require any communication at all. So before the entire process of federated learning starts, we can simply compute xi, and then we can start the process. For each client I, we define the algorithmic parameter alpha I, which is in between 0 and 1. And these will control the level of personalization that we have. And also they will tell us what is our communication budget for this level of personalization. So for each function fi, we will define fi tilde as the new function, which is defined as follows. So fi tilde of x, where x here will represent a shared model. It will represent the information that will be shared among the different clients and with new clients. And it's the loss fi on this alpha I x plus 1 minus alpha I xi. So it's like this weighted average of x and xi. And here, xi is the optimal model, again, like it's the optimal model in fi, the local empirical risk minimizer. And alpha I is the personalization parameter for the ith client. And finally, the FLIX formulation is minimizing x and rd, the average across all of the clients of f tilde of I of x. So we find the best x that minimizes the average of these losses of alpha I x plus 1 minus alpha I xi. And from here, we can start seeing why this would be good, because if I can find good x on these clients and I get a new client, then for this new client, I can, let's say we get client n plus 1, I can compute n plus 1 and then immediately apply alpha n plus 1 x plus 1 minus alpha n plus 1 for some alpha multiplied by x n plus 1. And I get a personalized model for this client with parameters that are already trained from from the previous clients. We let X star be the minimizer of this problem. So it's the minimizer of the FLIX formulation, this formulation. Let's say it is minimized at X star. Then the personalized solution that we deploy on each client is finally Ti of X is alpha I X star plus 1 minus alpha I Xi. And this is the solution that we will finally deploy. So this is like an affine function composed with our original functions, but in such a way such that we can always incorporate all of the information from the optimal local model Xi. And we can pre-compute Xi without needing any sort of communication, so it is relatively cheap from a federated learning perspective. So now we study some properties of FLIX. The first one is that it is efficiently solvable. If the function fi is li smooth, then f tilde I is alpha I squared li smooth. And by smoothness, we mean that the gradient is Lipschitz. So the difference between the gradient of x and the gradient of y is upper bounded by li multiplied by the distance between x and y. So this is the first thing. And this is good because this means that we do not lose the property of smoothness. Similarly, if the function is mu I convex, then tilde fi is alpha I squared mu I convex as well. And by mu I convexity, we mean that this relation holds fi of x is greater than or equal fi of y plus gradient f, this should be I of y, multiplied by x minus y plus mu I over 2 x minus y. So if mu I is equal to 0, this is just convexity. If mu I is greater than 0, this is strong convexity. And here we are saying that we preserve convexity and strong convexity, both of them, up to a constant alpha I squared. So by the previous two properties, this is simply like a new sort of empirical risk minimization problem. And it is smooth when the original problem is, it is convex when the original problem is. So we can apply standard methods to solving FLIX, and we can still get fast conversions for them. We don't have to develop new method, and we can use the wealth of existing methods. So like gradient descent, various reduced methods like SVRG, or whatever your pick of acceleration or other tricks. So the second property of FLIX is that we can adopt our problem to communication. So like going back here, observe that when the alpha i's are equal to 0, this problem is completely solvable by simply using like local models. And when alpha I is equal to 1, it's kind of the other extreme. We have to communicate a lot to solve this problem. And by controlling the magnitude of alpha, we can accommodate the communication budget that we have. So, for example, if alpha I is on the order of square root of epsilon, then we can solve the FLIX problem in one communication step. So we can, if we compute this weighted average of the different local models, where the weights are scale as alpha I squared Li over n L alpha, where L alpha is this average of the smoothness functions of the f tilde, then this will solve the problem up to accuracy epsilon. If alpha I is small enough, it is as small as square root of epsilon. And for alpha I greater than that, we can still accommodate communication budgets. It will just depend on the specific algorithm that we use to solve FLIX. Um, and now, like the other big thing is personalization. Does FLIX make sense for personalization? So in order to understand this, we will discuss like some of the methods that people use for personalized federated learning and see if like FLIX can get some of the benefits of these methods. So there are two methods which we will discuss, PFL and MOMO. And many other methods exist. I'm not claiming that these are the only methods, far from that, but these are the ones that we discuss here. And we do include some discussion about other methods in the paper. And so, for example, there's this nice paper by Yishai Mansour, Mary R. Mori, Jairo, and Ananta Tirtha Suresh, which gives, let's say, a more statistical approach to the problem. And there's also like Yuer Deng, Mohammed Mahdi Kamani, and Mehrdad Mahdavi on adaptive personalized federated learning, which is which gives us similar but not the same formulation as we're having here. Now, PFL, it goes by many names. And a lot of papers have studied it. So there's this paper by Philip Hansley and Peter Richter, federated learning of a mixture of global and local models. And this is like our main starting point with this work. There's also like many others who have studied it. So like this paper, personalized cross-silo federated learning on non-IIT data. And there's this also this paper of Dito, which can be seen as a generalization of this method. And a variant of it is personalized federated learning with moral envelopes. Kind of like many of these, they have relations between each other that hover around the same formulation, which is the PFL one. So this is the formulation. We have n different models for n different clients, and we are minimizing. This should be the average of fi of xi plus lambda over 2 xi minus x bar squared. So excuse me, this should have included an average here, but yeah, so we are minimizing the average of these new losses, which are the loss of fi and xi plus a regularization parameter that controls the distance of the xi from their mean. So x bar is the mean of the xi. It's 1 over n sum I xi. And the interesting thing about PFL is that we can show that local SGD or federated averaging is simply plain SGD applied to this objective. So in Hanseli and Richtari here, like this is one of their findings that at least a sort of approximate local SGD is simply plain SGD applied to this objective. So studying this objective can tell us something about like why people use local methods. And one of the main things in PFL is that it does variance regularization. So here what we mean is that the variance of the optimal models for a certain lambda from their mean, they decrease as 1 over lambda. And of course, this makes sense because we are explicitly regularizing it here. But this also means that we are converging to very specific solutions, which are perhaps different from the ERM solutions. And we can see that through the lens again, like this is what local methods are doing. They are solving this variant of ERM. So we can actually show that FLIX also does variance regularization. So if we denote the variance by var of a bunch of vectors, and T1 through Tn are the personalized solutions we eventually deploy, like that we had defined earlier. So these are the TIs. It's alpha I x star, where x star solves the FLIX problem plus 1 minus alpha I xi. So if these are the deployed solutions, then we can show that if all the like for simplicity, if all the alpha I are equal, then the variance of these vectors from each other is upper bounded by 1 minus alpha squared of the variance of the minimizers from each other. So kind of by increasing alpha, we are reducing the variance of these vectors in a way similar to what we get here by increasing the lambda parameter. So of course, at alpha equal to 1, all of these models end up being equal, because then we're just solving the ordinary ERF problem. So the point here, or the takeaway point here, is that we get this variance regularization. We get the benefit of variance regularization that PFL does, and that by extension local methods are doing. But we don't have to use any local steps. In fact, we simply pre-compute the minimizer of each function before training starts, and we get the exact same result. So we kind of don't even have to involve the different nodes in local computation at all. And if computational power is plentiful, this is feasible, or as a like local computational power. If the cost of communication is much higher. So the second method that we discuss is MUML, and MUML prepares a model for fine-tuning. So in our setting, the MUML loss is the average of Fi applied to X, like we denote by XKGD, K steps of gradient descent on this objective starting from a point X. So we want to find a point X that minimizes the loss on Fi after K steps of gradient descent using Fi. This was introduced by Chelsea Finn, Peter Abiel, and Sergey Levin in this very famous LastNL 2017 paper. So often we cannot really use K large because in order to solve this problem, we will need to differentiate through the gradient descent trajectory. And that is difficult when K is large. So we often simply use K equal 1. So here we get this average of 1 over n summation I Fi of x minus gamma gradient Fi of x, where gamma is some step size parameter. So here we're simply saying find an x such that after one gradient descent step, we get after one gradient descent step using Fi, we get a good solution. So the reason why, the reason why we want this is because we want an initialization that can allow us to do fast adaptation. So if we
I'm
have
appearing here, if I may, because there is a question by Konstantin Pulachenko. So I believe you can ask, Konstantin.
Thank you. Thank you. So in the FLIX, in the non-convex analysis, should xi star be exact minimizers or stationary points? Because you mentioned 2 slides ago that it should be minimizers.
Yeah, minimizers in the context of convex functions, but for non-convex, they can be just stationary points.
Okay, and the paper contains both convex and non-convex analysis.
So the paper right now on arXiv, it just contains the convex analysis, but we will, we're extending it with the non-convex analysis.
Okay, thank you very much.
You're welcome. Yeah, so again, the MUML objective is we want to find a good initialization such that we can adapt quickly using gradient descent. For k equal 1, this is simply Fi of x minus gamma gradient Fi of x. And as I said, a few slides earlier, this objective is non-convex, even if the original functions are convex. And it's not even generally smooth. You have to impose more assumptions on your function to get that this is smooth. but it works quite well in practice. So we would like some of the desirable properties of this objective. So like the reference again for the analysis of this objective is this paper by Ali Reza Falah, Arya Muhtari, and Assos Dalal from ASTAS 2020. Okay, so in order to think about like how to get the benefit of MAML, we can consider quadratic objectives. So for quadratics, we have fi of x equal this half x transpose ai x minus bi transpose x plus ci. And ai here is assumed to be a symmetric and positive definite matrix. So this is a convex quadratic. And we can show that the solution gradient descent does finds after k steps is this xk is I minus gamma ai raised to the power of k x plus I minus the same matrix raised to the power of k xi. So of course, when k goes to infinity, then this matrix, when we choose the step size to be smaller than the operator norm of ai, then this goes to 0 and this goes to 1. So this is a sort of averaging, like matrix valued averaging. So again, like here we have a matrix Ji, and this is the I minus gamma ai. And when we choose the step size properly, this has norm smaller than 1, strictly smaller than 1. So when you raise it to the power of k, it becomes very small. And this is the MAML formulation here is simply going to be fi on this solution, because like the MAML solution is fi on x after k steps of dd, and here we can actually find x after k steps of dd in closed form. So the main takeaway point here is that we have an averaging matrix of small norm. And the FLIX objective is we simply replace this averaging matrix by a constant. So we are finding some approximation to this. We are still finding like a good initialization that we can do personalization with, similar to the MAML objective. And when k is particularly large, then we can prove that the difference between this and alpha and some alpha I can be small if we choose the alpha I properly. And this should come as no surprise, because when k is large, this simply acts like it becomes closer and closer to simply like emphasizing the xi. Yeah, so the takeaway point here, we can see FLIX as approximating the ideal MAML objective, but with constants instead of matrices. Of course, the caveat here is that we have already shown this for quadratics, and this approximation can be lossy. But we are finding a good initialization based on the properties of the functions, such that we can do fine-tuning quickly, and the fine-tuning is of this form. Of course, if we replace alpha I by a matrix, then we can get that there's no approximation, it is exact, but then we need more parameters. So we kind of have to strike a balance between how many parameters we have to choose. So
there's yet another question by Rafal. I believe you can unmute yourself, Rafal.
Yeah, so I just want to quickly ask for clarification. What do you mean by initialization?
Okay, I mean like the X represents shared information between the clients, right? So if X is my starting point, this is the information that is common to the clients and that I want to give perhaps to a new client. So this is what I mean by initialization. I mean that if you get a new client and you have already like an X, then you can easily, like by computing something like this, you can find a fine-tuned model for your client. Does that answer your question?
Rafael might be speaking, but he's
Yeah,
muted.
sorry, I
Can't
got
hear him.
for some reason. Thank you. Yes.
Okay. Yeah. So like the thing is, like MAML is a method that finds a good initialization in the sense that we get FI. We are minimizing the expected loss on the clients when we like after we do k steps of gradient descent from a starting point X. So MAML is all about like finding a good initialization point that I can use if I get a new client. And this is exactly like when we use k equal 1, this just means that I want something that performs really well after just one step of gradient descent. And this is what we mean by initialization. Okay, thank you, Rafael. So now we ask the question, how do we solve this problem? And we can use any off-the-shelf method again, because we have a formulation that that preserves properties like smoothness and/or convexity. So gradient descent is one example, like distributed gradient descent, in which we have like we update the model as xk plus 1 is equal to xk minus gamma over n summation I alpha I of the gradient at this xk of fi. This is simply like differentiating through the FLIX objective. And the good thing now is that because we preserve convexity and smoothness, then this converges linearly for strongly convex objectives. So there is no need for any tricks to get this to converge linearly. It just does. And for local methods, that is usually not true. So for local methods, we usually get sublinear convergence. So here we're simply saying that we can get like the same benefit as local methods, like this variance regularization and such, but with fast convergence and simply by pre-computing the xi. And we can look at many other methods, such as compressed gradient descent or Diana. And for example, here, this is gradient descent. We here use gradient descent and compare it with Diana with the rent case specifier. So this is using like some sort of quantization, like stochastic quantization. And this is a logistic regression problem. So we can see that we can solve the problem quicker using Diana or gradient descent, but these are just examples. The underlying point is very simple. We can use whatever algorithm we want to solve this problem and get analysis for it. Like for example, until now, like the analysis of say accelerated federated averaging or accelerated localized GT is very difficult. But we can simply use acceleration here without requiring that, while still guaranteeing that what we have is a good finds a good initialization or fine tuning, at least approximately, or that it tunes the variance of these models. So we have performed some experiments for FLIX because, of course, this is a new method, new formulation.
Now
so
I would have one question, if I may. So on the previous slide, you had two plots.
Yes.
Could you comment on why there are two plots?
So these are for different alpha. Okay. So these are like basically this is for alpha is equal to 1, which is just the ERM problem, and this is for alpha is equal to 0.1. And the whole thing is just to show that changing alpha changes your convergence speed, and this should not really come as a surprise. But yeah, that's it. Like alpha is a parameter that we have to choose, and that changes kind of like how fast the algorithms can converge. So these are simply the two plots. They're just for different alpha.
All right. So one thing, if I may, I would just add one point of clarification here for others.
Yeah.
And which is that the speeds, the slopes look pretty much identical.
Yeah.
But what really changes is that the starting point becomes better if alpha is smaller, and this is because the formulation personalizes more.
Yes, so like the speed, so like since this is strongly convex optimization, then the speed is usually dependent on kappa, because this is like and the conditioning here is if all the alpha are equal, then the conditioning will just be like the original conditioning that we started with. So like if we go back, we have that our new smoothness constant is the sum I alpha I squared Li divided by sum I alpha I squared mu I. So if the alpha are equal, then these cancel and we simply get the old conditioning. If the alpha are not equal, I think the slopes would be different, but this is not the case here. But yeah, like the constant term multiplied by the slope, yeah, it's the difference because of what you said. Thank you, Peter.
There is a question by Ilyas Fatkulin. You can ask.
Yeah, hi, Ahmed. Hi, Peter. I was wondering here, loss, like definition of the loss here on the plot, it also depends on alpha, right?
Yes, it's the FLIX formulation loss.
Yeah, it's FLIX formulation loss. Okay. So like my point is that maybe it's not only like initialization helps, but also like since we're changing the loss, it will also affect the picture here, right? So it's not so clear.
That's right. I mean, like if you evaluate this on, like, let's say the ERM loss, then you will get also like a different situation, but like the graph of training will look the same because this is the graph of training, right? Like this is not
Yes.
yeah, so maybe it will not decrease the ERM loss much, but yeah, for this loss it will decrease.
And since I mentioned this comment about initialization, and since Ilyas asked about it, I wish to say one thing here, if I may. And that is what I meant to say is that yes, the loss is different, because if alpha is smaller, the loss tells you you're personalizing more, okay? But that means since you're personalizing more, the smart initialization that Ahmed talked about just happens to then be closer to the solution of this new formulation, and that is why everything is shifted downwards. And this is where the communication efficiency comes from. Ilyas, could you?
Yes, I see. Yeah, but then like what would be like another question is,
Anupam, could you unmute yourself? Unmute yourself because we can hear some background noise. Okay, thank you. Ilyas? Yeah, there was not, yeah, I don't know where the noise was coming from, but it was coming from somewhere. Okay, I will unmute Ilyas again. So Ilyas, you can unmute yourself now because I allowed you to.
Yeah, hello, can you hear me now?
Okay, so there was not Anupam, it's background noise with you there, Ilyas, but yes, we can hear you.
Yeah, I'm sorry for background noise, yeah. But at the end of the day, like another question would be like, what is the right measure to compare these two methods, like with alpha 0.1 and alpha equals 1, right? I mean, how to measure the personalization? Like what is, like what is like, how should we evaluate final result? Thank you.
Right. So like in order to evaluate, like this is a more complicated problem than we like. The main thing here is actually like the problem we're really caring about at the end is pretty simple, which is statistical generalization on each of the clients on the client's own dataset, right? So whichever gives us eventually the best, like the personalized solution that gives the best generalization at the end, this is what we want. So these curves, these are training curves. They're not meant to show generalization, but the experiments that I'm going to discuss next are about generalization. So ideally, we would be able to keep, like, we care about the generalization loss, but of course we cannot we cannot evaluate that directly because we do not have access to all of the data. So if you're asking, like, what is the holy grail of evaluating such a loss, that would be the generalization error. Does this answer your question?
Okay, so now there's
Yeah, thank you, Ahmed. Yeah.
thanks, Ilyas, for the question. There's a question by Anupam. Anupam, you can unmute yourself and ask.
So it's actually related to what Ilyas was talking about. So imagine that all the clients are training a hyper personalized model. So maybe alpha is close to 0. So does it affect the convergence, or again, I mean, on the X we are estimating that the global model,
Yeah, so like you'll be able to converge a lot quicker. In the sense that, like, the slope will be the same, but like your initialization is going to be very good. Simply the weighted average will get you very close. So like let me go back to that part. So yes, here it is. So here we're saying that if the alpha I is on the order of square root of epsilon, then we can find an epsilon optimal solution in just one communication step.
but that doesn't mean that will have the minimum generalization loss, right?
Yes, I mean, it doesn't necessarily mean, yeah, it doesn't necessarily mean that, but like we don't really know how to minimize the generalization loss directly, so we have to use these let's say secondary ways of handling it, such as MAML or PFL or this method FLIX. Like if we had access to the distribution on each client completely, of course, then you could just solve the local problem on each client, but we don't. So we have to kind of like take care of the distribution shifts between the different clients, but at the same time find still be able to do some sort of optimization.
Okay, all right.
Thank you. So yeah. Let me go back to the. Okay, so one of the generalization experiments is using this convolutional neural network on the MNIST database. And here we just compare against the solution found by using federated averaging. And we can see that, like, for some alpha in between, like neither 0 nor 1, neither of the extremes, we can improve upon Fed average. And this is a non-convex subjective. This is not convex. And yeah. Another experiment is using the Stack Overflow data set, where we have like either 2 clients or 50 clients. And we divide the data among these clients from the original data set. And then we apply multi-class logistic regression. And if the metric is the top 5 recall, then again, we see like that alpha in the middle, like neither 0 nor 1, neither of the extremes of ERM or fully individual training can help us a lot. Even compared to like existing methods such as FOMMO and Reptile for that are used in personalized federated learning. And the details for these experiments are in the paper. So the message of these experiments is really that we're just trying to show that if you use alpha somewhere in the middle, then usually you can get better generalization than simply using alpha is equal to 0 or 1. All right, so this is the end of the talk. Are there any questions?
Thank you very much, Ahmed. So there's a question by Konstantin Mishenka. So he asked it in the comment section, but Konstantin, you can unmute yourself and just ask directly. Okay, so he can't. So I will read the question. So Konstantin is asking, so alpha equals 1 is ERM, right? Then why FLIX with alpha 1 works better than for mammal and reptile?
I mean, for mammal and reptile are not solving ERM. Like they're solving a different problem. So sometimes the ERM can be better than using them. Because also like these methods were not developed for federated learning. They were developed for multitask learning, but yeah, so like they were developed in the context of you are getting a steady stream of new clients that you're going to use. But here we're not doing that. We're actually testing on the same clients, but with like distribution shift between the different clients. So in that case, sometimes you can simply do better by using ERM. And this is not in both experiments. This is only in one of them. I think it depends again on your data set. So when you divide it to two clients, you get that they do actually perform better. But this division with 50 clients, they do perform worse. And that is a good question.
Okay. Any